Hello guys, thank you for joining me today. I am making a presentation for a midterm project that I have for NSC 505. My name is David Capobianco, and we're doing a presentation on technical barrier for nuclear power in space. A little disclaimer, I have done this recording over and over. This is probably my sixth time already. And I had technical difficulty after technical difficulty, especially when you're recording a long thing. It tend to the computer type can freak out when I'm recording. So what I'm gonna do is I'm going to do maybe 2 3 slides and then cut the recording and then piece it together at the end because I can't keep doing these presentation over and over again um, I um, until I go crazy because there's just technical difficulty over and over and over. So let's get into the presentation. So I'm going to be putting this presentation on YouTube so that everyone can kind of watch it and learn from it and get maybe the information for it. This is for my class, um, but I'm going to be talking to the general audience of people who on YouTube so I can teach them about the technical barrier for nuclear power, and who knows if this help them get into this program or get them interested in this, it's a plus or whatever. Um, so I'm a little tired because I did record this 7 times already, 5 times already. This is my sixth time, right? So we're gonna go through this. So the first off, disclaimer is that this is kind of my favorite topic. I love space. My background is actually was in space system engineering. I went to Johns Hopkins University for a master program in space system engineering. I went for a semester. I dropped out of Johns Hopkins because I got the bill for the 2 classes that I was taking, and it was actually more than the entire degree to get the master's degree at Oregon State University. So that's why I decided to leave Johns Hopkins University. And also, I didn't see a good job prospect for me in astrophysics, in space system engineering, as much as I would in radiation health physics. And for those who don't know, I'm doing this project for radiation health physics, a master in radiation health physics at Oregon State University. It is for short, health physics. So if you don't know what that is, it can be described as nuclear physics or nuclear engineering with a focus in healthcare and radiation protection. All right, so that's for the general audience. Let's go to the next slide. So, introduction. Right, so as space exploration advances, the need for reliable power source become critical. Nuclear power offer a solution, but development in space and deployment in space it present a significant challenge. To overcome these barriers, it's essential to have safe and efficient use of nuclear power in space, and nuclear power can offer a lot of benefits that other type of um, um, traditional power sources might not. My brain's a little fried, so bear with me here. So as you go through this slide, you're gonna see a lot of picture like this one is from the video game called Elite Dangerous. It's my favorite video games. I love playing that game. It's a 1-to-1 scale of this universe, and since this is a 1 credit course, I thought I would kind of have fun with this presentation and kind of bring in science fiction, because science fiction and science fact is only differ by discovery in science development, right? So, and as you go through, you're gonna kind of see that this game is actually based on as much of real physics as possible, right? So, like I said, this is like an example. This is a space system, right? And it has a few space solar panel in the back, but that's definitely not enough. So, if you kind of have to think harder, it's probably use nuclear power to power it, right? So either fusion or fission, probably fusion, because hydrogen is probably more abundant in space, and this takes place like around 2,000 years in the future, right? And So one of the example is that this space station rotates. So you can see that ring. That's where people would live in the habitat. So it would spin and create a artificial gravity, right? That way, by using centrifugal force, right? So the table of contents. So we're gonna go through. So the introduction. So that we already talked about. Reliability in harsh condition for nuclear power plant, mineralization, radiation shielding, and nuclear propulsion. Right. So this is the content that my professor actually laid out as what we could use as an example. I like what she put out. I find that this topic is very interesting, so I decided to go with it. And this is going to be a broader explanation. We're not going to go into deep science nitty gritty. It's going to be a broad presentation of overall. This is a 1 credit class, and I kind of want to have fun with it. Right, hence why all the picture from the video game. So, as you can kind of see, this is the third picture from the video game, and if you kind of think, hey, is this an excuse for him to play video games? Is this project an excuse for maybe? But so why nuclear? And I'll explain the picture in a little bit. So why nuclear? So the distance from the star is extremely important, right? So when it comes to traditional way we generate electricity in space, so usually we use solar panel, right? But we could also use let's say combustion engine to launch things into space. The reason that that's not efficient or reliable is that we're going to run out of fuel eventually, right? And nuclear can last for a very, very long time. And we'll talk more about her Curiosity in a little bit, which is a rover on Mars. But let's say, why not solar? Solar is so great, right? Well, maybe you're doing a mission on a very far off planet like Pluto or Neptune, where sunlight is very, very limited. It could cause production problem. So energy production from the star is really, really not that much from there, and it's probably not enough, especially when you're going to have to do long distance mission through those region of space. Also, let's say even closer to the the star, like in our solar system, the planet of Venus is pretty relatively close to the sun, a lot closer than we are. And so let's say even if the planet is blocking the star, like if there's during the nighttime or we're on the other side of the planet, that the planet blocks the sunlight or the starlight, the solar light, then we're not getting a good power from or we're not getting any type of power generation from the star in that case. So it's a very inconsistent power in that case. And also I would say ability to find fuel. So for fuel, come down to this picture, and I explained this picture many times, so I'm a little tired. So what's happening here is that in this picture we're in a spaceship called a Python in this game, and we're going close to the star, and what we're doing is fuel scooping. We're doing a fuel scoop. So we're launching our fuel scoop, and we are catching hydrogen from the star to refuel our fusion reactor. So it would be heavier type of hydrogen, so deuterium or trillium, right, from the star would be used to then generate nuclear fusion inside the spacecraft. Hence why I use things from the video game, because it's very much relevant, because the science fiction from that game is actually based on science fact. So consistency, survivability in hard condition. So nuclear power plant may be a little bit easier to maintain in space. Let's say if we're going to a different type of mission like asteroid belt or the asteroid rings, where you want to do some probing in there, but the solar panel require huge surface area. So from that, it could cause, like, you might have debris, space, um, rocks that could hit it and cause damage to those kind of component so that it wouldn't be usable. So this offers alternative to having that, and that could be one of many examples that I could bring up. Nuclear fuel has very high energy density, and it lasts a very long time, right? So a very long lifespan, like we're going to talk about in Curiosity. Reliability in harsh condition, right? We'll talk about the screenshot in a little bit, but space-based nuclear power system must operate in extreme environment, right? Temperature fluctuation, microgravity, extend period, and operate for extended period of time without failure. For example, ensuring reliability in these harsh conditions require advanced material robust system, redundancy, and innovative thermal management solution, and we'll talk about that in a little bit. Overcoming these challenges is critical for sustaining long duration space mission safely and efficiently. And this picture is of my rover on an exoplanet, right? So we landed on that exoplanet where there's a abandoned base over there that someone set up. But this kind of highlight the dangers of space. So let's say, like, in that type of planet, it doesn't have the electromagnetic field that the Earth has to fight off against solar flare and solar weather that may be caused from that star right there. So that is one of the example of harsh condition in space. Of course, also gods know what is also on that planet that could be harsh condition, like desert storm or sandstorm or different kind of things. But I know this exoplanet does not have an atmosphere, so that is not a issue. But it could be temperature issue and as well as and something else. Okay, let's move on. Let's get into challenges of nuclear power in space. So the first thing is radiation exposure. So there's a lot of radiation in space, and also radiation that may be caused from the nuclear generation as well. The first class I took at Johns Hopkins was space weathering, right? So we learn a lot about the major cause of space weather is mainly from our star, right? So solar flare, solar thing. So it needs to be able to protect against that, and also so that it doesn't cause a malfunction in the nuclear reactor itself. And it also needs to protect the occupants from radiation exposure from the nuclear power plant that it's, or the nuclear plant that is generating as well. So it has to have there's extreme temperature variation in different part of space, and even in the same planet, there could be a huge radiation variation. Like, let's say Mercury, so the surface that's facing the sun is a lot hotter than the back of the dark side of Mercury by a lot, by a few hundred kelvins actually. So that's something that if we were to do a mission to, let's say, those type of exoplanets, it would be something that we need to take into consideration. Also, nuclear power plant generate a lot of power and also a lot of heat. So because of that, we need to be able to disperse this heat and reduce the heat so it doesn't overheat. And that has a huge challenge, especially in space, especially in dead space, where there is a vacuum of space and you can't rely on convection or conduction to disperse heat. So that's something that to definitely think about. So the only type of heat dispersal would be radiation, right? So the way to think around it is maybe like internal heat management system like convection and conduction would have to be done inside the spacecraft itself. My microgravity, so things tend to work differently in different type of gravity. So fuel, liquid, for cooling, fuel reaction, they tend to have different type of effect in lower microgravity, and especially in space there's no gravity. In like even in planet like Mars there's lower gravity than here on Earth, and let's say even we go to Jupiter or Saturn, you're gonna need to have there's gonna be a lot higher gravity over there as well. So that's something that we definitely need to take into consideration while doing research and development into creating probes and power plant for that type of applications. It has to have a long operation lifespan. You can't have the life support going out, right, in space, because it could be very detrimental. Material durability would be something that has to be looked into for because there's not going to be Amazon in space, so you're going to have material that's durable enough to be able to survive in extreme conditions and the harshness of space, and to be able to shield from radiation and heat for the occupants of the spacecraft and the electronics as well. Thermal management, we talked about that. Shielding requirements, so shielding from space, shielding from the power plant itself, from nuclear reaction to begin with. It should have system redundancy, making a lot of system so that for fail-safe purposes, so if something goes out, there's a backup system. Autonomous operation. When I was taking radiation protection class, something that I really took out from it is humans are unreliable. People take shortcuts, and having AI system or inbuilt mechanical system so that to safeguard and fail-safe and to monitor these things could be very beneficial over having human beings do it. Launch and development risk, so if something were to launch from Earth or something like that, it needs to be able to withstand, the component needs to be withstand the type of G-force and launch condition to go into space, or if it was to be built on a space dock, right? Attached there is a picture of a schematic of a nuclear power plant. Kind of shows the challenges of making small power plant, because there's a lot of things that goes into building it, and I actually had to cut out part of it because I couldn't fit it onto the slide. Next slide. So there's a few solutions for that, and that could be think of advances in material coding, just making sure that my recorder there is actually recording, so I don't need to do this again. I have a bit of PTSD from that, but anyways, let's go on. Advanced material and coating. So using radiation resistant, heat tolerant, and corrosion proof material to enhance durability for reactor components, as well as shielding it from outside radiation. Redundant system and fail-safe implements backup system. Reduce redundant electronics and autonomous fail-safe mechanism to ensure continuous operation in case of malfunctions. Automated monitoring and AI diagnostic, right? Like I said in the last slide, that humans are unreliable. They take shortcuts, so having a computer do it might be actually better. Modular reactor design so that it could kind of fit and it's repairable, right? It's easy to repair, so because if it does break, it could pronounce really, really bad things for the occupants or even the spacecraft itself. Redundant system and fail-safes, we just kind of talked about that. So anyways, then this kind of nuclear power plant. We could also talk about things for spacecraft and things for habitat on spacecraft. So I'm trying to make sure that I talk about it because I did this presentation so many times. I didn't know if I say this yet or I did not. So if I did not, you know why. But it is also could be something that you need to think about when you're putting things onto a planet like Mars as well, because and the things will change as the environment changes, right? The requirement will change, the solution will change. Let's go on to miniaturization. So miniaturization is a critical challenge in developing space-based nuclear power system, as traditional reactors are too large and heavy for practical use in space mission. Engineers must design compact, lightweight reactors that maintain high efficiency while meeting stringent safety and durability requirements. Reducing size without compromising performance involve advancement in fuel technology, heat management, and shielding material. Successful mineralization will enable nuclear power to support long-duration space mission by providing reliable, high-output energy to form that is feasible for transport and development. Right, and the big thing is it has to be small enough to be able to transport, put into spaceship, and we'll talk more about this. So we'll talk more. So we'll get into Curiosity. So Curiosity is the rover launched by NASA. It's currently on Mars right now, and the interesting thing about it is it used nuclear power. More specifically, it used nuclear power radioisotope thermoelectric generators, RTG. Some people call it nuclear batteries, right? To get power, and it uses heat from decaying plutonium to generate electricity. And it was projected to last over 14 years. It's still there, and it could be there for longer than 14, 15 years. Who knows? Right. Another current technology we talk about is small modular reactor (SMRs). Right. Small modular reactors offer a promising solution to space-based nuclear power by providing compact, scalable, and efficient energy source. Their small size and modular design may help make them smaller to transport, assemble, and integrate into spacecraft and planetary habitat. SMR also enhance reliability in incorporating passive safety feature and advanced fuel design and improve performance in hard space environment by reducing weight and increasing flexibility. SMR could play a critical role in sustaining long-duration mission and advanced deep space exploration. And it doesn't always have to be in spacecraft. It could also be creating this reactor, assembling it and transporting it to like an exoplanet or a station or a space habitat somewhere like that. And as the technology stands right now, it's a little too big for a spacecraft. It's tend to be when I was doing research for it, it is probably very feasible for, let's say, a Mars colony or a moon colony or something like that. All right, let's get on to radiation shielding. I did make a lot of the funny part is that when I was making this presentation and the first time I presented it, I had a lot of jokes and I had a lot of fun when I was making it. Hence why I was making a lot of video games references and stuff like that. But this is the 6th recording, and I am just too tired for that right now. So it's going to be a little more grand than my first presentation, and I am beating myself up that didn't go through. But radiation shielding. So radiation shielding is essential for protecting astronauts and spacecraft from harmful radiation in space, including cosmic rays and radiation emitted by nuclear power system. Without proper shielding, prolonged exposure can lead to several health risks and damages to electronic systems. Developing lightweight yet effective shielding material is major challenges, as traditional method adds significant mass, which is critical constraint in space mission. Innovative solutions such as advanced composite material, magnetic electrostatic shielding. So for this, I made or I used a picture, not from the video games, and this is the sixth time I'm doing it, so I promise the first time it was funnier. But so like on Earth, there is a electromagnetic field that is being or magnetic field that's being generated by the Earth core, which is the molten core that we have, um, and that created a magnetic field that protects against a lot of space weathering that would be coming from the sun, like solar flare and stuff like that. In space, we don't have that type of protection, so we're gonna have to rely on our own ingenuity to protect the spacecraft or space equipment while we're up there. So technology in shielding. So there's a few different types. So we'll get through it. So shielding from radiation from the environment, like I'm gonna repeat that, and radiation from protection in radiation shielding from radiation from the power plant itself. So we could do traditional shielding material, right, which is lead and tungsten. They are a high density material. They are effective against gamma radiation, but usually they're too heavy for spacecraft application. Launching it into space, they're very heavy, but you can definitely use it for creating like using it in constructing power plant in a base that is already a habitat on another planet or something like that. So I'm gonna have a hard time pronouncing it. English is not my first language, but polyethylene, effective at blocking cosmic ray and secondary radiation. They are usually commonly used in astronaut shielding, like in their suits or on a spacecraft. So it's a technology that's already currently being used. Next, we have composite materials, so hydrogen-rich polymer, right? Such a they are usually very effective at absorbing neutron radiation. And you have multi-layer composite, and they're combining different material to optimize protection against various radiation types. So like usually weave or they kind of stack together, right? Like what is shown in this picture right now. There's a few advanced shielding technique. So one of it is electromagnetic shielding. So same principle as having a magnetic core or a metal core for Earth, where we have a magnetic field that protect against space weather. This is the same thing. We could use, we could generate electromagnetic field around a habitat or a spacecraft that we're going through. So that could kind of create an area of protection, right? And plasma shields, which is an experimental technique using artificial plasma cloud to absorb or deflect radiation, right? And if this is actually very new technology, experimental, but that's actually some of the technology that used to explain science fiction in space, such as like Stargate, or even in Battlestar Galactica, or even in the game that I played, which is Elite Dangerous, is used to for deflective shield to protect against incoming damage or whatnot. So that's one of the cool things about combining science fiction and science fact, because they're not too far apart, right? So next, self-healing material. So regenerative polymer, right? Like material that can repair itself. Include damage from that can happen from like outside forces or inside forces, radiation pinning from inside the reactor itself. We can have regenerative polymer. It's very new technology. It's actually being developed right now, and sometime they're using it to see if they could kind of cure scratches in cars. Technology is actually out for that. nanostructured materials, so engineered at atomic level to provide higher durability and resistance, right? So very nano material. When I was doing my undergraduate degree, one of my professor his specialty was in nanotechnology, so this is probably his bread and butter. Water and so water shielding. So it's water-based shielding. So a lot of people don't realize that water can actually act as a really good source of radiation absorption and radiation shielding. So it does a very good job at absorbing cosmic rays. So that's something with water, and water is very abundant. You can kind of refuel or mine it from space. A lot of asteroids has water, so very abundant in space for sure. It's abundant just as helium is. Well, helium's low, or hydrogen, my bad. So nuclear propulsion, and now we're finally getting into places where I have my my screenshot from video games. So I don't know if I included in this lecture or not, or this roundabout, but I didn't make a joke that is this project an excuse for me to play video games, and maybe a little bit, but yeah, it's like, sorry, I can't take care of the baby right now. I'm too busy doing my project for school. So that's a great thing. So anyway, nuclear propulsion is a promising technology for deep space exploration, offering high efficiency and safer travel time compared to a conventional chemical rocket by utilizing nuclear reaction to generate thrust. These systems can significantly reduce mission duration, lower astronaut exposure to cosmic radiation. There are two main types of nuclear propulsion. There are two main types. There is nuclear thermal propulsion (NTP), which heat a propellant like hydrogen, and it shoot it out in the back to produce thrust, or nuclear electric propulsion (NEP). A lot of you guys would probably know it more as ion propulsion, or an ion thruster, which is used to generate electricity for ion thrusters. Advancement in nuclear propulsion could enable faster, more effective mission to Mars and beyond that. Nuclear thermal propulsion, NTP, is what we're going to get into. So the basic concept of NTP is that making sure that my recorder is working. So, but the basic concept is it heats up a propellant, like let's say a liquid hydrogen, into and then it shoots it out in the back, right? And then thermal Newton law of motion takes into account, like you shoot something out, there have to be an equal and opposite reaction, right? So that's the basic concept of it. It has high efficiency. It's higher efficiency than a chemical rocket, because chemical rocket, it's easy to run out of fuel. It has a lot of thrust, a lot more thrust than this, but it's a lot more efficient than that. It can reduce travel time because of that, because of continuous thrusting or longer fuel consumption. Or fuel efficiency, it can go for a longer duration, which can reduce travel time. So challenges in fuel selection, right? So the reactor usually use uranium or plutonium or something like that to generate the energy, but to heat up the fuel source could be hydrogen, which is quite abundant in space, in this universe actually. So like, go back into the concept of fuel scooping, right, where you can scoop fuel hydrogen from the star, which can also be used for fuel and also used as a propellant, right? In this case, once the technology get to that part, but that's a future technology that we could kind of talk about. But the one of the big concern is thermal management, right? Heat generated in a spacecraft, especially in a vacuum of space, it's really hard to dissipate heat. because you can't rely on convection or conduction through through the outside forces. You have to have convection and conduction within the ship itself, and then the only type of thing that you can rely on is radiation, right? So that's the very inefficient way of releasing heat or dissipating heat, and so there has to be a technology that we need to develop to cool down the engine and propulsion system if we were to make this feasible. A fun fact with that picture right there as a screenshot, it was of a screenshot of my ship, the Anaconda, and a fighter that I had on board that I launched so that I could take this shot. The lore in Elite Dangerous for the spaceship is they use NTP propulsion, right? Nuclear thermal propulsion. They shoot hydrogen from the back, and it makes sense because they do fuel scoop hydrogen, right? So radiation shielding will be needed, right? So when you're generating this type of nuclear power and shooting hydrogen out of the back, you need to have active shielding to protect viable compartment and even the people inside it from danger. So there's still testing and development hurdle. NTP is still in its early development. It still needs extensive ground testing, and it's still a long way from practical use right now. Right, potential, but once it does, once we can figure out all the kinks of it, it has very high potential for space exploration for sure, and space application. So nuclear electronic propulsion, and NEP. So the basic concept of it is that it is ion propulsion, right? It shoots ion particles out the thrusters. So they use electricity to create ion charges and shooting ion particles and shooting them out, right? They're extremely efficient. They're extremely efficient. They're way more efficient than even NTP, right? Making sure my recording is still working. But they provide much lower thrust output, right? Even and comparing to combustion engine, they are not even comparable to that. They produce very low thrusts. But fun fact is that when I was doing my capstone at Liberty University for my bachelor degree in physics, my final capstone was in ion propulsion. I did a presentation on ion propulsion, and so this is something that I'm a little more familiar with. But when I was doing that project, people in IIT were struggling to keep thrust for producing enough thrust for a paper airplane to remain airborne. So we're still a long way from it, but it is actually ideal for space mission right now, because when you're in space, there is no friction, right? There's no friction in space because you're in the vacuum of space. So when you're traveling in space, as long as you can keep doing continuous thrust, you'll keep on accelerating, or you'll keep on that acceleration, so your velocity will keep increasing. So it doesn't take a lot of power, so it's very power efficient, and like everything else, it does need radiation shielding as well. So this brings me to the end of the presentation. In conclusion, space-based nuclear power systems offer a promising solution for a long-duration space mission, but their development come with significant technical challenges. Overcoming this issue relate to reliability in harsh condition, miniaturization, radiation shielding, and propulsion is essential for ensuring safe and efficient operation. Advanced small modular reactor, SMR, we talked about, nuclear thermal propulsion, NTP, and nuclear electronic propulsion, NEP, like ion propulsion, present a viable pathway to addressing these challenges. Continuing research, innovation, and international collaboration is a key to succeeding in the future, right? And so that we could have exploration beyond Earth, right? Because for us as humanity to succeed, we do need to kind of branch out and not rely on this planet only to survive. So we're coming back to the last slide and the last screenshot, which is the Cobra Mark III as a module of this beauty of a spacecraft. It is not a screenshot, sadly, but it is an artwork from that video game. Right. I had fun making this slide, and I had fun presenting it the first time. So I would like to apologize. There's a lot of and ah for these presentations. I'm very tired. This is my 6th presentation. I've been recording this over and over and over again. I was not in the same mood as I was when I first made this video or made this presentation, and a lot of jokes and a lot of humor that I had in here had all kind of left. But anyways, I hope you guys enjoy this as much as I enjoy making the slide. I enjoy putting in a lot of science fiction and my video games into it because it's fun. And like I would like to remind you, this is a 1 credit class. And bye-bye.